Okay, I'm going to move into something a little more mathematical now, but don't worry, we're not actually going, this is going to be some algebraic reasoning, but it's not actually, we're not going to plug any numbers in, and I don't know if that makes it better or worse, but that is what we're going to do. So, okay. We talked about equilibrium, we talked about the idea that this equilibrium occurs where the forward and reverse reactions are happening at the same time. However, some forward reactions are inherently faster and some are slower, and some reverse reactions are inherently faster and some are slower. So I don't want you to think that equilibrium means that the products and reactants have equal concentrations. That's not necessarily the case. The rates are the same, but the concentrations aren't the same. Some reactions have their forward reactions so fast, so much faster than the reverse, that you end up with a whole lot of product built up and not very much reactant. Some reactions have a very fast reverse and a very slow forward reaction, and end up with a lot of product and not very, or a lot of reactant and not very much product at equilibrium. So the ratios at equilibrium, how much product and reactant you have, varies from reaction to reaction to reaction. Okay? It's not they have equal amounts. The equal in equilibrium is talking about the rate, not the amounts. So we have each reaction has what's called an equilibrium constant, and this is a value that represents how, like, where along that continuum the equilibrium is. In other words, the equilibrium may be very product heavy, may have a lot of product and not very much reactant. The equilibrium may be very reactant heavy, have a lot of reactant and not very much product, or maybe somewhere in the middle. So, this is a numerical value that characterizes the equilibrium, the relationship between concentration of products and reactants at equilibrium. So, this is the following just generic reaction, right? So the A, B, C, and D are the reactants and products. J, K, L, and M are the chemical coefficients. I think your book uses slightly different letters, but it's not really relevant. It's the same exact formula overall. The equilibrium constant ends up being this. K, which is our symbol to represent, that's representing the equilibrium constant, is the concentration. So when we put something in brackets like this, this is saying the molar concentration. So the concentration in molarity. So the molar concentration of C times D, but C and D are each raised to a power equal to their coefficient. So C raised to the coefficient that it has in the chemical equation, D times the molar concentration of D times its, or raised to the power of its coefficient over A, blah, 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 so on and so forth. The main thing to remember is it's products over reactants. So, what's important here is thinking about what a very large K would mean and a very small K would mean. That's where we're going to go with this. We're also going to need to know how to write these expressions, so I'll show you in a minute. Okay, so some important points to point out. Square brackets refer to molar concentration. Concentrations of products are always in the numerator. Reactants are always in the denominator. Coefficients are the coefficients in the balanced equations are the powers. KEQ is the abbreviation for equilibrium constant. Concentrations are only given for solids and liquids. Now, this is the big key. Or for solutes and gases, I'm sorry, that's what I meant to say. Solids and liquids are omitted, or rather, they're considered to be 1. Any solid or liquid is 1 in the concentration. It goes away. It's not part of the equilibrium expression. Because you can't really have a concentration of liquid water, right? Concentration, it would just be moles per liter, and it would be the same based on the temperature, right? Based on its density. So it doesn't really make a lot of sense. So it just goes away. It just becomes 1. So any solid or solid or liquid becomes 1. Solutes and gases, aqueous and gases, are used as their concentration. We'll see examples. So, for example, the equilibrium expression for this would be K equals, so it's products over reactants. So here's how I'd write it, and I'm going to ask you to do this as well. Concentration of N2 raised to what power? The power would be 1 because there's just a 1 in front of it, an understood 1 in front of it in the balanced chemical equation. Times the concentration of H2 raised to the third because of the 3 right here. Over, so it's always products over reactants, NH3 to the power of 2 raised to the squared. We're not doing anything with numbers yet. We're not plugging any numbers in. We're just looking at what the expression would be. So again, products over reactants, where K is the equilibrium constant, and the values in brackets would be the concentrations of species at equilibrium, not any other point. This has to be at equilibrium. All right. Take a moment and practice writing these. Okay. K is going to equal, so it's products, SO3 squared over SO2 squared times O2 raised to the 1. Down here, it's going to be Br2 cubed times PCl3 squared over PBr squared Cl2 cubed. There it is. Oh, my 3 didn't really come out. There we go. I think I got it right. There we go. Okay, I'm going to have you do one calculation. This is literally just a plug and chug kind of thing. So go ahead and try this problem. All right, so now we have to write the expression first. We have to figure out what we're plugging in where. The expression will be concentration of N2 times concentration of O2. Each of them raised to the power of 1 because there's nothing up here. And then NO squared. So when we do all this, we're going to do N2. We look for the concentration for N2. So it's N2 is 0.024 molar. O2 is 0.024 molar. And down here is 0.0026 molar squared. One thing, this is a good time for me to point out, that, actually let me do the calculation first. I got 85 as my answer. Notice that the units will be molar times molar over molar squared. It may work out that they cancel exactly. It may work out that they don't. But the nature of K, for reasons I'm not going to get into, this is our only thing that we've really talked about outside of, say, percentages or ratios that doesn't, and it is a ratio, effectively, that it doesn't have units. K is unitless. So equilibrium constants are unitless. So at this temperature, at the temperature that we've figured out this equilibrium, the equilibrium constant for this reaction is at 1,000 degrees is 85. So let's talk about what that means a little bit. So the magnitude, the number, the value of the equilibrium constant gives us information about about the ratio of products to reactants at equilibrium. So how far towards completion, exhaustion of the reactants, does the reaction get when the equilibrium is reached? So if the equilibrium constant K is really big, remember, it's products over reactants. So this means that there's a lot of products and very few reactants. If it's small, if it's a small number, like a negative exponent, then that means there's a lot of reactants and very little products. So we have some terms to describe that. And so that was the numbers, these numbers for each equilibrium, for each reaction. is the equilibrium constant. We're going to talk about something called the equilibrium expression, or sorry, the equilibrium position, which is an abstract qualitative idea about how far, about the relative amounts of reactants and products, just expressed qualitatively in a different way. And we're kind of taking the abstract idea that the reaction is proceeding from left to right from reactants to products. So if K is very big and there's a lot of products, we say the equilibrium lies far to the right, right? It lies to the right because that's where the products are. It got pretty far to the right. If the equilibrium constant is very small, we say it lies to the left, right? So there's more reactants and products. The reaction didn't get very far. You had a lot of products to start, or reactants to start with. You built up a little bit of products, and then the reaction just hit equilibrium, and you couldn't get very much product.